Hello everyone, welcome to our class. In this lecture, we will continue to introduce some properties of simple linear regression, and then I will show you how to estimate a real data set with simple linear regression. After that, we will move on to introduce a more general case, which is the multivariate linear regression. So recall that in the last class, we start to introducing the simple linear regression. We showed what is the problem setup and how to estimate unknown coefficients in the simple linear regression. And after that, we would like to discuss how to assess the accuracy of your coefficient estimates. So in today's lecture, we will continue to discuss how to assess the accuracy of your coefficients, as well as how to assess the model fitting accuracy for a simple linear regression. After that, we will discuss an example based on a Boston house pricing dataset, and after that, we will extend our concepts of simple linear regression to a more general case which involves more than one predictors, and we call that a multivariate linear regression. Okay. So recall that in the very end of last class, we discussed that we would like to assess the accuracy of your coefficient estimate, right? So as long as we fit a simple linear regression from a least square estimator, right, we obtain an estimator of beta 0 and beta 1, and we denote them as beta 0 hat and beta 1 hat. In particular, beta 0 hat is an estimate of your intercept coefficient, and the beta 1 hat is an estimate of your slope coefficient. So besides we obtain the particular values as our estimates, we also want to assess how accurate these two estimates, right, compared with the truth. So we would like to analyze the bias and variance side of these two estimates conditioned on the random sample you have obtained. So the first one is we have shown that we can have the unbiasedness, which is a very nice property for your estimates beta 0 hat and beta 1 hat. So the unbiasedness simply means if you calculate the conditional expectation of your estimate, say the conditional expectation of beta 0 hat given this random sample x, you will find this conditional expectation equals the true parameter beta 0. And also for the slope estimator beta 1 hat, the conditional expectation of beta 1 hat given the sample x equals to the truth beta 1, right? So this is a very nice property, which means your estimates are aiming the true target. So besides unbiasedness, we also would like to know for a given random sample, how will your estimators beta 0 hat and beta 1 hat as two random variables depend on your random sample spread towards your truth beta 0 and beta 1. So to understand that, we would like to analyze the variance, or we call it the standard error for your two estimators beta 0 hat and beta 1 hat. So for beta 0 hat, we can calculate the conditional variance of your beta 0 hat given your random sample x here, right? Or we can write it as the square of the standard error of your beta 0 hat, right? So which is just defined as the square root of your conditional variance, okay? And also you can calculate the square of your standard error of beta 1 hat, which is defined as the conditional variance of your beta 1 hat given this random sample x, okay? For either case, we can show that the standard error of beta 0 hat and standard error of beta 1 hat roughly depends on two items. The first item is the sigma square, right, which is the population variance of your approximation error epsilon, right, which is an unknown parameter to us. And on the other hand, this sigma square is actually scaling with respect to a quantity of order 1 over n, right, which depends on your sample size n. So you can see that the scale of your standard error for either beta 0 hat or beta 1 hat depends on the scale of the variance of your approximation error epsilon. and also it will scale down with an increasing number of your sample size n, right? So for a larger sample size n, you would expect a smaller standard error of your estimates. And when you have only a small sample size n, you would expect to have a large standard error of your estimates. Okay. And one remaining question we left in the last class is the sigma square is actually an unknown parameter to us, right? So in practice, in order to calculate the standard error of beta 0 hat and the beta 1 hat, we need to estimate this unknown parameter sigma square, right? And the estimating of sigma square is actually a very standard problem in least square estimators, okay? So in practice, one can estimate the sigma square by the sample variance of your residual Ri, right? So recall that Ri, the residual of the ith observation, is simply defined as Yi minus your fitted linear model, right? Which can be considered an estimate of your approximation error epsilon I, right? And this estimate is known as the residual standard error and is defined by the following formula here, right? So basically, we can estimate this unknown parameter sigma by calculating the residual standard error, which is defined as the square root of your residual sum of squares divided by the degrees of freedom n minus 2. And recall that the residual sum of squares is defined as the summation runs from I equals to 1 to n, and for each term in this summation is the square of your residual Ri, which is defined as Yi minus beta 0 hat minus beta 1 hat times xi, and then taking square, right? And this whole term is divided by n minus 2, right? So recall that when we calculate the sample variance of one random variable, we need to divide the degrees of freedom n minus 1, right? Because for the sample variance, we already need to know what is the sample mean of that random variable. And knowing the sample mean actually will give us a minus 1 degrees of freedom from the original degrees of freedom n. And for this case, we need to divide the true degrees of freedom as n minus 2, right? Because for the calculating of the residual sum of squares, we already know two parameters, beta 0 hat and the beta 1 hat, right? So recall that in the last class, we showed that beta 0 hat and beta 1 hat admits a closed form depends on your random sample xiyi for I runs from 1 to n, right? So as long as you know beta 0 hat and the beta 1 hat, you need to minus 2 degrees of freedom from your sample, okay? And after we have obtained this residual standard error, which is used as the estimate of your sigma, right? We can just replace sigma square by its estimators, sigma hat square, right? In the calculating of the standard errors of beta 0 hat and beta 1 hat. So after obtaining the sigma hat, we should be able to calculate the standard errors for beta 0 hat and beta 1 hat, okay? And in the follow-up discussions with a little bit abuse of notation, we will still use SE of beta 0 hat and SE of beta 1 hat to denote the standard errors of beta 0 hat and beta 1 hat. But here we will replace the unknown coefficient sigma square with its estimate sigma hat square, okay? And another question, okay, one would like to ask for the simple linear regression model is, besides we can assess the accuracy of your coefficient estimate, right? So another very important question is, for this fitted linear model as a model overall, okay, how well can this model fit your data set, right? So how well can you predict your data set with this given linear model? So which is equivalent to ask you how to assess the accuracy of your model, right? So to answer that, one need to define some proper quantities to assess the accuracy of your linear regression fitting, right? So there are actually two commonly used quantities, which I will introduce in the follow-up slides. Okay, the first one is called the residual standard error, or RSE for short. Okay, and another very helpful quantity for assessing the accuracy of the model is called the R-squared statistic. So first, I will introduce you what is the residual standard error. So as we have introduced in the previous slide, the residual standard error, which is actually the one quantity we use to estimate the unknown coefficient sigma, right, which is the standard deviation of your approximation error epsilon, right? And this residual sum of and this residual standard error can also be used as a quantity to assess how good you fit this linear model. So recall that this residual standard error is simply defined as the square root of your residual sum of squares divided by n minus 2, right? So we can understand the intuition of residual standard error by looking at this equation here, right? So when we calculate the residual sum of squares, we are actually calculating the overall lake of fitting for your linear model, right? So how to understand this sentence here? You can think that we will actually predict the response variable yi by the linear model fitted by us, right? In other words, we will estimate yi by yi hat, which is defined as beta 0 hat plus beta 1 hat times xi, right? So in other words, we can review each term in this bracket as yi minus yi hat. Okay, so you can see that the bracket actually means the difference between the truth yi and your fitted value yi hat and taking the square. And then by summing them over I from 1 to n, the residual sum of squares is actually calculating this thing, right? Which is the overall misfitting of your linear model, right? So the larger the residual sum of squares, the worse your model can fit the real data set, right? And when the RSS is very small, which means your y hat are very close to yi in an overall sense, that means your linear model actually fits your data set very well, right? So in that sense, you can say the residual standard error is no more than just a linear transform, is no more than just a transformation of your residual standard error, right? So you just divide by a constant and taking the square root. So in other words, when residual sum of squares is large, your residual standard error is large. And when your residual sum of squares is small, your residual standard error is also small, right? So in other words, we would expect when the residual standard error is small, which means your linear model fits your data very well, right? On the other hand, when you have a large residual standard error, which means your linear model does not fit your data set very well, right? So therefore, we can consider this residual standard error as an indicator to measure how good your model is being fitted, right? Okay, so even though the residual standard error provides us a measure to assess the accuracy of your model fitting, right? It is actually an absolute measure of lack of fit to your linear model, because, right? So if we review the definition of your residual standard error, so actually the residual standard error depends on the sample size n, okay? And also it depends on the scale of your yi, right? So you can think that for a data set, okay, of size n, right? And if you use only half of your random sample to fit a linear model, right? So which means you are fitting a linear model with a sample size of n divided by 2 instead of n itself, right? So then when you calculate the residual sum of squares, the summation runs only from I equals to 1 to n divided by 2, right? So no matter how good your fit your linear model, you will have a smaller residual sum of squares simply because you have a smaller sample size, right? And to our intuition, when you use a larger random sample, you would expect to reduce the bias and variance of your fitting, and you would expect to have a better fitted linear model, right? So which means the residual sum of squares as well as the residual standard error only provides an absolute measure of your model fitting. It's actually not a good quantity to be used to compare the fitting performance between different models, because this quantity itself depends on your sample size and also depends on the scale of your y, right? So if you imagine that you measure the yi with a different unit, which means, for example, you measure the yi by meter instead of centimeter, okay? Then you can imagine that you have the scale of yi being downscaled by 100 times, and you, even for the same fitted linear model, you will have the residual sum of squares being downscaled by 1 over 10,000, right? So then you will have a much smaller residual standard error, even if you are fitting the same linear model, okay? So to overcome this issue caused by absolute measure by using the residual standard error, right? Another probably more relevant property in comparing different estimators or comparing different models is called the R-squared statistic, right? This R-squared statistic provides an alternative measure of fit, and it takes the form of a proportion. So actually it's a relative measure instead of an absolute measure, okay? And the R-squared can be calculated by the very simple form like this one here, okay? So the R-squared is simply defined as the ratio, okay, between two terms. The first term is the difference between your total sum of squares, measure the residual sum of squares, and divide by total sum of squares, right? And the total sum of squares is simply defined as the yi minus y bar, where y bar is just the sample mean of your yi taken square and take the summation from I equals to 1 to n, right? So if you divide this summation by 1 over, if you divide this summation by n minus 1, this is actually the sample variance of your yi, right? And the residual sum of squares is simply the form which we defined in the previous slide, right? And you can simplify the calculation of R square. So if you divide TSS by TSS and minus the ratio between RSS and TSS, you will have the R square can be calculated by 1 minus the ratio between your residual sum of squares and your total sum of squares, okay? And this total sum of squares can be understood as the amount of variability inherent in your response variable y before any regression is performed, right? So you can see that R squared is actually 1 minus the ratio between residual sum of squares and the total sum of squares. It actually measures the proportion of variance of your response variable being explained by the linear model. So it actually always takes some value between 0 and 1 and is independent of the scale of y, right? And one can actually understand the R squared as a horse racing between predicting the data set with your linear model fitted by least square estimators, and predicting your model with simply the sample mean of y, right? So if you treat this y bar as a special estimator of yi, so you can think this TSS as the residual sum of squares by predicting each yi by the sample mean of y, right? Okay, so after we have introduced the problem setup, the estimation, as well as some assessing accuracy properties of simple least square, so let's consider to apply that to a very interesting data set. And this data set we want to discuss today, it's called the Boston house pricing data set. Okay? And the data set just collects the median house price and many related variables over 506 neighborhoods around Boston. And for our example here, we only consider a simple linear regression scenario. So we only pick two important variables from the data set to fit a linear model. So the response variable we will use for this example is the median house price, or we show that as MEDV as the label in the data set of each neighborhood. Okay, so we have 506 different observations of this response variable. Okay, on the other hand, the covariate we pick to predict the response variable is the percent of households with low socioeconomic status, or LSTAT, which is the label of this random variable in the data set. Okay, so our goal is try to fit a simple linear model between the response variable and this covariate. Okay, and in particular, we are actually considering the following mathematical form of your simple linear model, right? So for each individual neighborhood, we have two values, yi, which is the median house price of this neighborhood, and we have a predictor yi is the percent of households with low socioeconomic status in this neighborhood. And we want to fit the following model: yi equals to beta 0 plus beta 1 times xi plus epsilon I, where beta 0 is the unknown intercept coefficient, and beta 1 is the unknown slope coefficient, and the epsilon I is the unknown approximation error. And we have this random sample observed over 506 data points. Okay, so now first let's have a peek at the data set before we really fit this simple linear regression. Okay, so here we just plot the scatter plot, okay, between our predictor x and our response variable y. Okay, and each red dot in the scatter plot represents a pair of values of x and y observed from one of 506 neighborhoods. So here I would like to pause for a few seconds to give you some time to have a look at the scatter plot, and what would you like to summarize from the scatter plot. So, and also I want to ask you a couple of questions here. So first, according to the patterns shown on the scatter plot, do you think it's a good idea to consider a simple linear regression model? Okay, and if so, what would be the relationship you expected to obtain from the simple linear model? And if not, what is the reason for you to think it's not good enough to consider a simple linear regression? Okay, so I will give you a few seconds to look at this data set and think about these two problems. Okay. Okay, so you probably have already have your answers of these two questions. So here let me just explain to you what I think should be the answers to these two questions about this data set. Okay. So first of all, we can actually draw some circles, okay, on this data set. So here is actually what I did here. So in general, for the majority data points in the scatter plot, we think there's actually a very clear linear relationship between x and y, right? So which is what I draw as this blue shaded area here. So all the data points within this blue shaded area exhibits a very strong linear relationship between x and y, right? And if we consider we fit a straight line like this over this blue shaded area, we would expect to have a positive intercept and a negative slope, right? Which means the response variable, the median house price, would be negatively associated with your predictor, the low socioeconomic status, which means for a neighborhood with less houses belongs to low socioeconomic status, the median house price would be high. And on the other hand, for the neighbors with more low socioeconomic status houses, the median house price would be lower. And a positive intercept also makes sense, which means no matter how many low socioeconomic status exhibits in this neighborhood, you would expect the house price still to be positive, right? Otherwise, you will have a negative house price, which does not make sense. However, we do have some other data points outside this blue shaded area. So here I roughly draw another purple circles here and here to indicate there are actually some outliers which may not be fitted very well by a simple linear regression model, right? So in other words, the linear relationship assumption may not be perfectly satisfied in this data set. There are many reasons of that. So one possible solution is that you probably want to introduce more predictors into this model, which may probably explain the response variable y in a better sense. Or you may consider some nonlinear models to fit this data set. But for this example, let's stick to the simple linear regression and try to see how well we can fit the relationship between x and y, even though there indeed have some outliers. Okay. So if we fit a simple linear regression between x and y, follow the least square estimation method, okay, we can calculate our estimate of the intercept parameter beta 0 and the slope parameter beta 1. Okay, as what we expected, we have a positive beta 0 head and a negative beta 1 head. Okay, and the straight line we fit for the simple linear regression model is actually being plotted as this blue line here, right? So we do see that this blue line is actually a little bit higher up here because we do have the impacts of these outliers, right? So if we ignore those outliers, we may expect a line in the middle of these clusters here. But we do have this blue line to be a little bit shifted up here, which is the impact of these outliers. Okay. And after we obtain our estimates of beta 0 head and the beta 1 head, okay, we can actually predict the response variable y by this linear model like this, no matter what new value of x you can observe for some other neighbors in this area, right? So for any given input of x, you would use this linear model 34.55 minus 0.95 times x to predict the median house price y associated with this input. Okay. And then after we fit this linear regression model, we would like to assess, right, how well we estimate these parameters, as well as how well we fit this linear model. Okay. And here we can actually assess the accuracy of this simple linear model. Okay. So based on the fitting model, we can actually calculate the residual standard error of this fitting model, right? And if we input the beta 0 hat and beta 1 hat over this random sample, xi and yi, we can calculate our residual standard error by this equation here, which is 6.216. Okay. And we can also assess how well we estimate these two parameters, beta 0 hat and beta 1 hat, by plot this contour plot of residual standard error, right? So in these two-dimensional plots, we use x-axis to denote the value of beta 0 hat and the y-axis to denote the value of beta 1 hat, right? And for each point on these two-dimensional plots is actually the residual standard error value corresponds to a given pair of beta 0 hat and beta 1 hat. And we use these blue solid circles to indicate the pairs of beta 0 hat and beta 1 hat which have the same residual standard error, right? And we actually, for each circle, it have a different amount, and when we shrink the radius of these circles, we would expect to have a smaller and smaller residual standard errors. And the smallest residual standard error is achieved by our discrete estimator beta 0 hat and the beta 1 hat, which is indicated as this red dot in the middle of the plot. Okay. And the best prediction results, which corresponds to the smallest residual standard error, is of course being obtained by fitting this linear model with this pair of estimates, right? Okay, so far we have showed you how to do a simple linear regression model for a given data set. So sometimes it's not enough to include only one predicting variable in your regression analysis, right? For example, in that Boston house price data set we have shown, we can certainly see that fitting a simple linear regression model is probably not good enough because there are some unexplained outliers in the data set, right? So we'll probably consider a more complicated regression model to fit your data set in a better sense, right? And one possible way is we still follow a linear model assumption, but we include more predictive variables in your fitting model, right? And then that's how we need to consider an extension of your simple linear regression problem, which is called the multivariate linear regression. Okay. And again, if we use this Boston house price data as the example, we have examined the relationship between the median price and the percentage of low socioeconomic status. Okay. We also have the data for the average room per house, the average age of house, crime rate, and so on in this given data set. So one very interesting question one would ask is, why not we include all those information for some other random variables available in this data set to see if we can achieve a better prediction performance compared with only use this one covariate, right? Okay. And then here, let's first briefly discuss what is the problem setup if we want to extend the idea of simple linear regression to a multivariate linear regression, right? So suppose that we have x1, x2 to xp as p predictive variables or p covariates in your data set, which you would like to use to predict one single response variable y. Okay, so Similar as the problem setup we used for a simple linear regression, we can consider the following very simple multivariate linear regression problem, right? So we just model y equals to beta 0 plus beta 1 times x1 plus beta 2 times x2 until plus beta p times xp plus the epsilon. Again, the beta 0 here is the coefficient which is used to describe the intercept of your linear model. And here, instead of having only one slope parameter beta 1, we have p different slope parameters or coefficients for each individual covariate x1 to xp. And also, we need to consider an approximation error term epsilon in this linear model, right? Okay, and here we just use xj, j runs from 1 to p, to indicate it's the p's predictor or p's covariate. And then the coefficient beta j actually quantifies the association between xj and your response variable y. And also we call beta j the j's slope coefficient in your multivariate linear model. And again, this epsilon here is the approximation error term, which can be considered as the difference between y and this whole linear function of x1 to xp. Okay? And suppose that by some way we obtain a set of estimates of beta 0 hat to beta p hat, we can actually predict our response variable y by replacing beta 0 to beta p, these unknown coefficients, with their estimates beta 0 hat to beta p hat. So we can predict y by y hat, which is defined as beta 0 hat plus beta 1 hat times x1 plus beta 2 hat times x2 until plus beta p hat times xp. So you can see that the only difference between multivariate linear regression and simple linear regression is for here we have p predictors and p slope coefficients. And you can consider simple linear regression as the special case with p equals to 1 of a multivariate linear regression problem. Okay? And similar as the simple linear regression problem, we also would like to discuss what are the underlying assumptions for a multivariate linear regression problem. So we can see that the assumptions we relied on to build a multivariate linear regression model is very similar to the ones we used for simple linear regression. So again, for the first one, we assume there's an underlying linear relationship, which is that we assume that the response variable y can be approximated well by a linear function of x1 to xp. And the second, we would like to assume the observations of your response variable y, which is the random sample y1 to yn, are independent with each other. And for the third one, we assume the uncorrelatedness between your predictor x1 to xp with your approximation error epsilon, right? Which means we assume the covariance between xj and the approximation error epsilon equals to 0 for, sorry, here should be j runs from 1 to p. And for the fourth assumption, again, we need to assume this homoscedasticity assumption, which is assumed that the mean and the variance of your approximation error epsilon are the same for all observations. And for the fifth assumption, again, we assume the error epsilon is normally distributed. Okay, so it's very easy to see that from assumption number 1 to assumption number 5, they are actually exactly the same as assumptions we imposed for simple linear regression case. But we still need to impose 2 more assumptions to the multivariate linear regression case, right? Because we have more than one predictors, right? And we need to make some assumptions to the relationship among these p predictors. Okay, so the assumption number 6 is called the no multicollinearity assumption, which assumes that the covariates x1 to xp are not highly correlated with each other. Okay, so what does this mean? Which means you cannot simply explain one of these p variables as a linear function of the other p minus 1 variables. So what will happen if this no multicollinearity assumption is violated, right? So for example, if we have only p equals to 2, okay, we have two covariates we use to predict the response variable y, and we consider a very extreme case, which is x1 equals to x2, right? Which means x1 and x2 are identical, or you can think that x1 and x2 are perfectly collinearity, right? Because x1 can be explained by 1 times x2 as a perfect linear function of x2, and on the other way, x2 can be explained as a perfect linear function of x1, right? And in that case, when you model y with both x1 and x2, right, you have the regression function y is defined as beta 0 plus beta 1 times x1 plus beta 2 times x2 plus epsilon, right? And in our setup, if we consider there's a perfect linearity relationship between x1 and x2, you will have x1 equals to x2, which means you can simplify your regression function for y as beta 0 plus beta 1 plus beta 2 and taking the bracket times x1, right? Because you can replace x2 simply by x1. So in that case, so instead of we need to fit 3 parameters, beta 0, beta 1, and beta 2 from this linear model, when x1 equals to x2, we actually equivalent to fit only 2 parameters for this linear model, beta 0, and another one is defined as beta 1 plus beta 2, right? So that will actually cause an issue, right? So when you fit this linear model, you only know the good estimate for beta 1 plus beta 2, right? But there are actually infinite possible ways to decompose the sum of beta 1 and beta 2 into two numbers. So in other words, you are not be able to identify beta 1 and beta 2 simply because x1 and x2 exhibits a perfect collinearity. So that will actually cause an issue for your fitting a multivariate linear regression. Okay. And the last one is we need to have the so-called low dimension assumption for a multivariate linear regression, which requires your sample size n to be greater than your dimensionality p, which is the number of covariates you imposed for this linear model. So this low dimensional assumption is necessary because when p is greater than n, we are not be able to solve this multivariate linear regression model unless we impose some other constraints. Okay, so we will have a closer look at this condition when we review the estimation of the multivariate linear regression. Okay, so now after we have introduced all the introduced the problem setup as well as all the assumptions for multivariate linear regression, so now let's consider how to estimate those unknown model parameters beta 0 to beta p. Okay, and the estimation procedure is actually very similar as what we did for simple linear regression, but we just extend that to this multivariate linear regression case. Okay, again, our goal is to choose a set of parameters beta 0 hat to beta p hat that can minimize your residual sum of squares of this linear model, right? And again, the residual sum of squares is simply defined as the summation I goes from 1 to n, and for each term is yi minus yi hat, which is the fitted value of yi, and taking the square. So each term just simply measures your estimate of yi, how close between the estimate of yi and the truth. And in the multivariate linear regression case, the yi hat can be replaced by beta 0 hat plus beta 1 hat times xi1 plus beta 2 hat times xi2 until plus beta p hat times xip, right? So you can just calculate your residual sum of squares by these equations here, right? As long as you know the set of beta 0 hat to beta p hat, you know everything you need to calculate the residual sum of squares in this equation. And our goal is to choose this set of values beta 0 hat to beta p hat, which can give you the smallest residual sum of squares. And the procedure to solve this problem is called the multiple least square regression problem. Okay, and the estimates are usually being called the multiple least square coefficient estimate. And unlike the simple linear regression, okay, which in that case we have only beta 0 hat and beta 1 hat, and we have shown that beta 0 hat as well as beta 1 hat exhibits a simple closed form solution. And for the multivariate linear regression case, our estimates of beta 0 hat to beta p hat also exhibits a very simple closed form solution, but it's better for us to view them in a matrix form. In the matrix form, you will have a really simple closed form solution for your unknown parameters. Okay? So first, let's consider how to rewrite this multivariate linear regression model in a matrix form. Right? Suppose that we observe a random sample of n observations, y1, x11 to x1p, right? Which is indicates as observation number 1, you have one value of y, and the p value of your p covariates in the data set. And also for the second observation, we just replace 1 with 2. And until we have n observations, right? The nth observation, we just replace 1 or 2 with n, okay? And instead of writing that in terms of p plus 1 numbers, we can write the multivariate linear model with this following very simple matrix form, right? So this boldface y is indicated as a vector of response variables, right? Which is just a vector, a column vector of y1, y2 until yn, right? So you notice that here is a transpose sign here, which indicates this is actually a column vector. Okay, so it's actually n times 1 column vector, and we write this boldface y to indicate it's the vector of y1 to yn. Okay, and then we will use this boldface b, okay, which is actually a p plus 1 times 1 column vector to include all the unknown regression coefficients from beta 0 to beta 1 until to beta p, okay? And this b is actually the vector of coefficients of interest, and we want to estimate b by solving the least square problem. And also we can collect all those values of x11, x2, x1p, x21 to x2p until xn1 to xnp in this so-called design matrix, which we use the boldface x to indicate that. So for the first row is actually the values we observe from the first data point, which have x11 to x1p, okay? And we add an additional entry 1 in the first column here is because we want to include the intercept beta 0 in terms of this linear regression problem, right? So recall that we'll have yi equals to beta 0 plus beta 1 times xi1 plus beta 2 times xi2 until we have beta p times xip, right? So you can decompose beta 0 as beta 0 times 1, right? So by including this 1 here, we actually be able to have x have an adequate size to multiply with this vector b, and we have the beta 0 times 1 to indicate it's the intercept parameter. Okay, so we will have this design matrix X is a matrix of size n times p plus 1, right? So we have n rows and p plus 1 columns. So the ith row indicates the value of x we observed for the ith data point, okay? And the jth column indicates the values of the j minus 1th random variable we obtained across n data points, because j equals to 1 is reserved for the intercept, right? And also we will have the last item in this matrix form linear model, which is E, which is used to as an n times 1 column vector corresponds to E1, E2 until En. So here I just use E1 until En to indicate the approximation error you obtain for each individual observations, okay? Then by rewriting the data random sample in terms of this matrix forms, right? We have the multivariate linear regression model can be expressed in a very simple matrix form, which is the boldface y equals to boldface x times boldface b plus the boldface e. Okay. And with this with this matrix form, we can express the multivariate least square problems in a very simple form, right? So what we would like to do is we want to figure out what is this value b hat, which is a p plus 1 times 1 column vector here, which is the vector that can minimize the residual sum of squares, which is defined as y minus x times beta, taking this L2 norm, okay? And this L2 norm is just simply defined for a vector, okay? It's like if you have a vector, say A, which is of size p by 1, and the L2 norm of A is just the transpose of A times A itself, which is considered to as the inner product of each element in this vector A, right? And for this case, right, recall that Y is a column vector of size n by 1, X is a matrix of size n by p plus 1, and beta and B is actually a vector of size p plus 1 times 1, right? So X times B is also a column vector of size n times 1, and the difference between Y and X times B is also a column vector of size n times 1, so you can take the L2 norm of that. And this argmean sign here just indicates you want to find the B such that this L2 norm is as small as possible, okay? And the above minimization problem can be solved by finding the root of the first order derivative of this L2 norm, right? This is equivalent to solve the following equation, right? You calculate the partial derivative of this L2 norm with respect to this vector B, and you want to set this partial derivative equals to 0, which gives you a equation here, right? And the b hat is actually the solution to make this equation holds. And by solving this equation, you are able to find the b hat, which is the minimizer of this loss function here, okay? And if we calculate this partial derivative here, it's just equals to minus 2 times x transpose times y minus x times b hat, okay? And by solving this very simple equation here, you will be able to give a very simple closed form of your vector of coefficient b, which is b hat equals to x transpose times x, and taking the inverse times x transpose times y, right? And one very simple way for you to check if it's a valid solution is you can check if the dimensionality of those matrices are matching with each other in terms of this matrix multiplication case, right? You should be able to have, you found the transpose of x is p plus 1 times n. For x is n times p plus 1, and taking the inverse of that, you have this whole term is of size p plus 1 times p plus 1, and for x transpose is p plus 1 times n, and for y is n times 1, right? So by multiplying these three together, you will have the size of B is p plus 1 times 1, which is the correct size of this coefficient vector B, okay? And then after we have reviewed this closed form of least square estimator B hat, we are able to use that to explain why we need to impose the low dimension assumption that n is greater than p, right? So in this case, right, we need to calculate the inverse of x transpose times x, right? And this x transpose times x is of dimensionality p plus 1 times p plus 1, right? And if we have n is smaller than p plus 1, this x transpose x will not be a full rank matrix. And in that case, this x transpose times x is not invertible, and we will not be able to calculate this ordinary least square estimator B hat, right? So this term is only invertible if we have n greater than p plus 1 in this case, right? So that's why we need to impose the assumption that n is greater than p, or n is greater than p plus 1, to make sure we have a valid closed form solution of your vector of coefficients B, okay? And this B hat is usually being called the ordinary least square, or ORS estimator of your vector of coefficients B, okay? So for today's class, we will stop here, and in the very beginning of next class, we will also introduce you how to assess the estimate accuracy of your coefficients, as well as the accuracy of your model fitting for a multivariate linear regression problem, okay?